We are Memphis Community University and we're back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. And today we're doing another advanced derivative topics, but it's actually going to build off an old one. Basically, we're going to take the topic of implicit differentiation and we're going to do questions that use implicit differentiation, mainly with tangent lines. So really what we're going to do is we're going to review implicit differentiation and then we're going to find some tangent lines based off implicit differentiation. So it shouldn't be the hardest lesson in the world because a lot of it will be review. We'll talk about the big mistakes when people take derivatives implicitly. Remember that taking derivatives implicitly just means that you're going to be taking the derivatives of functions that are in terms of the other functions. So you need to remember the chain rule. So the main example is that the derivative of y cubed, for example, isn't just 3y squared when y is a function of x, when you're trying to find dy dx. Actually, the derivative of y cubed is 3y squared times y prime. So if you need to, definitely go check out our old implicit differentiation videos before this one, because this is the next level. Today we are going to review implicit differentiation. We're going to find some second derivatives. We're going to take implicit differentiation of different variables to be careful. And then finally, we're going to end on some hard tangent line questions where we're going to find where the tangent line is horizontal and vertical. So just a lot of different little questions involving implicit differentiation. We might as well get started. So again, what this video is today is implicit differentiation revisited. So implicit diff, I call it imp diff, implicit differentiation 2. Let's do this the second time. So the first question is sort of a recap. So what we're going to try to do is we're going to try to find the tangent line. So find the tangent line of this function right here, of x squared minus xy of f of x that equals y, where y satisfies this equation, and we're going to have equal 4, and it's at the point x is equal to 1. So a nice little bit of review of implicit differentiation. Notice that we do have to use implicit differentiation in this case because we have two variables here. We have x's and y's in it. And implicit differentiation allows us to take the derivative without having to isolate y, which is definitely the best case scenario. So this is our first review of implicit differentiation. Remember that again, the derivative of anything that has y's need a y prime. And secondly, the main thing that students mess up when they take these derivatives is they're not careful with the product rule and they're not careful with negatives, things like that. So let's take this derivative together. So the derivative of x squared is regular, so it's just the power rule. It's going to be 2x. Actually, let's read the question first. So the question isn't actually implicit differentiation or use implicit differentiation. The question is actually about tangent line. So remember that for any time you have a tangent line, which will come up in this video, what you need is you need a point and you need a slope. So in this case, we're going to write point first. Let's find the point before we find the slope, where the slope will require the derivative implicitly. So what's the point? Well, it looks like they only give me one coordinate of the point, 1 comma something, x is equal to 1. But all I have to do is plug in 1 into this function and I'll be able to find the y coordinate pretty easily. So it's going to be 1 minus 1 times y equals 4. Again, I'm plugging in 1 for x. 1 squared, of course, is 1. So it looks like when I solve this, I get y is equal to negative 3. If you bring over the y, subtract over the 4, negative 3. It looks like we have our point. Now we can go for implicit differentiation because remember that the derivative is given by y prime or dy dx. And that is going to be found implicitly because again, we're not trying to solve for y. So what's the derivative here? Well, this will be the derivative step. And the derivative is going to be the derivative of x squared is just 2x using the power rule, taking the power, dropping to the front. And here's where again, students start making mistakes because they have this product. So you do need to recognize this product. The derivative isn't, for example, minus 1 times y prime. You do have to employ the product rule. And keep in mind that the negative will go on both sides of the product rule. So I like to think of it as not x times y, but negative x times y. Those are my two functions of the power rule. So let's do it. Derivative of the first, so it's just going to be minus 1. Keep the same the second thing, so it's just y. Then we keep the same the thing we took the derivative of. So in this case, it will be minus x. And then finally, the derivative of y is unlike the derivative of x because the derivative of y is that y prime. Finally, what's the derivative of 4? Just be careful, of course, it is 0. So looks like we want to isolate y prime. If you watched our previous implicit differentiation videos, what we would do is we would do a lot of algebra steps to isolate y prime. For example, we would add over this thing and then we would divide by x. But because we already have our point, once you take the derivative, one tip that we offer is that because we're finding the derivative at a certain point, just plug in the x coordinate and the y coordinate where they go, and it'll be a lot easier to solve with y prime, because usually students can deal with numbers better than they can deal with variables. So again, if you need a formula for y prime, like in the next example, you do need to isolate y prime. But if you have a point, you can just plug in everything. So for example, keep in mind that there are two coordinates, so you have to plug it into the correct space. But this is the x value, this is the y value. So it looks like when we plug in, it's going to be 2 times 1 minus 3. So again, you have to be very careful with these negatives, but it's minus -3. Then it's going to be minus x times y, so it's just going to be y prime equals 0. So if we do a little bit of math, looks like it's going to be 5 minus y prime is equal to 0. So y prime is equal to 5. Finally, for the very last part, what we're trying to do is find the equation of the tangent line. Remember that you need point of slope, where the slope is the derivative, but we already found that, so we are ready to go for the answer. So I believe the answer is going to be endpoint slope, y minus the y coordinate, so it's going to be y minus -3, so that's why it's +3. And finally, it's the slope times x minus the x coordinate. So it's 5 times x minus 1. So this is a pretty basic level of an implicit differentiation question. Not many new things from our previous video. The key though was, of course, taking this derivative very, very slowly, potentially using product rule in this case. That's what we did. Another thing to keep in mind is that it saves you a little bit of time if you're finding the derivative at a certain point, is once you take the derivative, plug in those coordinates to the point, and it just makes it a little bit easier in my mind just to solve it. But pretty easy question. Tangent lines need point and slope or slope of the derivative, and in this case, we employed implicit differentiation. So let's do a little bit of a harder question. Let's try to take second derivatives now. So when you take second derivatives, as we're going to see, what you have to do is you have to first find the first derivative, and then you can find the second derivative. So let's do that. So let's say we're taking the derivative of something like y to the 4th plus 2x squared minus equals to 3 plus, I don't know. We can just do plus equals 3 to keep it a little bit simpler. So again, our question isn't going to be just find the first derivative. What we're going to try to do in this question is also find the second derivative. And in order to find the second derivative, unfortunately, you cannot go from the original function to the second derivative. You first need to find the first derivative, of course. So that's going to be our goal here. So we're going to try to find the first derivative, and then we're going to find the second derivative. So let's get going. So the first derivative here, well, again, the derivative of things with y need y primes because you're taking the derivative with respect to x. So this won't need any sort of prime action, but this one will. It's the nice little power rule. You take the 4 to the front, and then you subtract 1 from the exponent, so it's 4y cubed. But again, please, just remember to multiply by that y prime. So in this case, it's 4y cubed times y prime. Then the derivative of 2x squared is a little bit easier because again, the variable is a little bit easier. So all you're going to do is you're going to take the 2 and bring it to the front. You're going to subtract 1, let the 2 and the 2 mingle in the front. So it looks like I think we're getting plus 4x. Because I don't want to confuse exponents and derivatives with primes, I'm going to write this as dy dx actually. Keeping in mind that, of course, dy dx is the same thing as y prime. So that derivative of y to the 4th is 4y to the cube times y prime or times dy dx. Finally, some people get so excited to take derivatives of variables that they forget that the derivative of 3 is 0. Just try to not make that mistake. That derivative is 0. So unlike the previous question, as we mentioned before, because you had a point already and you can just plug it in because you only cared about the derivative at that one point, what we did in that question was we just plugged it in and we didn't isolate. But in this case, because we need to find a formula of the first derivative, we do need to isolate dy dx. So in this case, dy dx looks like it's going to be, well, negative 4x, because we're going to bring over this 4x, and then we're going to finally divide by 4y cubed. So this is going to be my first derivative. And then we're going to go for the second derivative. Keep in mind, though, there is a nice general rule of thumb. One thing you can do is you should simplify each derivative before you take the next one. Same thing with if you are applying multiple L'Hopital rules, for example. It's just easier to simplify constants and then they'll go away in the next derivative. So you could certainly take the derivative of this guy right here, but I'm going to make one step. I'm going to divide by these 4's because in my next derivative, there will be no 4's and it'll be a little bit easier to manage. So in this case, it's going to be negative x over y cubed. So it looks like that's my first derivative. Now I'm going for my second derivative. So I look at this and I have to remember derivative rules, of course. I have to see a product. Sorry, I don't know what I'm saying anymore. I see a quotient, so it looks like I have to do the quotient rule, unfortunately. So it's low d high minus high d low over low low. Keep in mind, though, that even when we take derivative of quantities that include y from the first derivative to the second derivative, we still have to employ implicit differentiation. So when we're taking the derivative of y cubed, it's not just going to be 3y squared, as you'll see. So let's do it. It's low, so low d high minus high d low over low low, that's quotient rule. So it's low y cubed times the derivative of high. The derivative of minus x is just minus 1, minus high, but it's going to be minus minus, so it's going to be minus minus, so minus high d low. And this is where the d low comes in. Again, it's not just 3y squared using the power rule. It is 3y squared times dy dx. So it's going to be 3y squared times dy dx. Furthermore, don't forget divide by low low. It is a common mistake, but when you divide by low low, it's going to be y cubed squared. So now what we need to do is we need to just simplify the question a little bit. Notice that we have a formula for dy dx. It's actually this thing right here. Dy dx is equal to this. So, and sometimes when this is a multiple choice question, what they're going to do is they're going to replace this dy dx with what it is. So we can simplify a little bit. Looks like this is just negative y cubed on the top here. Then we have x cubed times 3y squared times negative x over y cubed. And then finally, we're going to divide everything. Keep in mind that this is not 3 cubed, it's 3 squared because of low, y cubed squared. So keep in mind that y cubed squared isn't y to the 5th. That exponent rule is you multiply the powers. So on the bottom, it's going to be y to the 6th. So basically, this is a closed form. I sort of ran out of room on my board, but you can certainly simplify this further if you want. For example, you can divide by y squared, this should be y. You can multiply this x and x together to be minus x squared. Then you can multiply everything by y and try to get rid of all these fractions. So I'm going to do that at least in my head. So again, it's going to be something 3x squared with a minus, negative 3x squared, y squared over y, that'll be divided by y, and then I'm multiplying everything by y to get rid of all the y's, or the fractions within fractions. So I think you're going to get negative y to the 4th over y to the 7th in the very end. But again, that's not the most important step. The most important step is just doing the derivative correctly. You don't have to simplify the derivative usually. So in this case, again, we are going from a second derivative. So what we did is we did a normal first derivative. We simplified the derivative before we went for the second derivative because that just makes our lives a little bit easier. We always want to make our lives a little bit easier. Keep in mind that when we took the second derivative, we did have to employ a quotient rule, low d high, minus minus, high d low over low low, or the minus is canceled. And then just as a one final step, because when we took the derivative the second time, we still needed to employ implicit differentiation, we ended up getting a dy dx in the numerator. And what we should do is take our original dy dx and just place it nicely where it goes so that we can have our answer in terms of x's and y's, just like normal in an implicit differentiation question. So this is the work. Again, kind of a hard process, or maybe not a hard process, but a tedious process. But if you're careful with your y primes, you should be good to go. So let's do a little bit of a trickier question that might be even easier, but it's trickier. So same sort of idea. Let's say we have different variables because oftentimes they switch up the variables, at least to involve dt's because you have times. So let's say we have a formula where we know that dp over dt is equal to p cubed plus 3p minus 2 or something like that. And what they're going to ask you is to find the second derivative. So again, it's an easier question than the previous question, because in the previous question we started with the original function. Then to take the second derivative, we first had to hit the first derivative, and then we could take the second derivative. In this case, though, they're being a little bit nice, because in this case, they're starting with the first derivative. So to find the second derivative, all I have to do is take one more derivative. But if you see this question, it's very, very easy to mess up. As you can imagine, as people go for the derivative, they're very confident with the power rule. So what they write is something like 3p squared plus 3. And you can imagine why people do this, because that's the derivative of x cubed plus 3x minus 2. But keep in mind though, what variable is playing the role of y and what variable is playing the role of x in this case? Well, it looks like y is being played by the role of p, because that's the numerator, the dy dx. This is dp dt, and t is playing the role of x's. So if this question were t cubed plus 3t minus 2, then it would be a normal derivative. So the derivative would be 3t squared plus 3. Unfortunately, this is not a normal derivative. This is like taking the derivative of y's, but it's not any more harder if you remember that step. So what's the correct derivative of p cubed? It's not just 3p squared. Just like the derivative of y cubed is 3y squared times y prime, the derivative of p cubed is 3p squared times db dt, or p prime. Same thing here. What's the derivative of 3y? Well, usually it's not just 3, it's 3 times y prime. So what's the derivative of 3p? Well, again, it's not just 3, it's 3 times dp dt. So it's going to be times dp dt. So then we're going to do the same thing as we did in the previous question. We have a formula for db dt, so we're going to substitute it in. We're not going to FOIL all this out potentially because it's not really the point of the question. The point of the question is recognizing you have to do implicit differentiation so you don't get tricked, because trickers get tricked. We don't want to be tricked. We want to trick them, whoever's giving these assessments. So again, the main thing is just recognizing you have to multiply by db dt. But once we substitute it in, it's going to be 3p squared. Let's see if we have enough space. Times this thing right here. Plus 3 times this thing right here. So again, anytime I see db dt, I'm replacing it with this polynomial. So it's going to be p cubed plus 3p minus 2. And that's going to be our answer. Again, if you really want to simplify this, you can simplify this by multiplying all of this out. But I don't feel the need to. All I wanted to justify and show you guys is that the derivative of this guy requires implicit differentiation because this variable is like a y. You see these a lot on differential equation free response questions at the very end of AB or sort of the middle of BC, where when you take that second derivative, people just do it very carelessly and they just write 3p squared plus 3 and then they're on their merry way. But unfortunately, you do have to employ implicit differentiation. So just be on the lookout for that when you have these different variables, and make sure you need to potentially multiply by y prime or db dt or whatever your variable is. But those questions are pretty easy. Now what we're going to do to conclude the video are 2 harder variant questions. Not, again, a hard-ish question, but it involves a lot of algebra and things like that. So let's get started with that. So we're going back to tangent lines. So what we're going to do is we're going to have this function right here, y squared equals, let's do 2x cubed over 3. And then we're going to have minus 2x plus 3. So the numbers get a little bit nasty in this question, but sometimes you got to get your hands a little bit dirty. But what we're trying to do is, if f of x equals y satisfies this equation, we want to find at what x does, if I can spell the word does, f of x have a horizontal tangent line. So again, we're going back to tangent lines, but it's slightly different than other questions. For example, in that first question, we were given an x value and we were finding the equation of the tangent line by plugging in that x value and that y value into slope to find the equation of the tangent line. But in this case, what we have is a horizontal tangent line. We already know the tangent line and we're trying to find an x so that f does have a horizontal tangent line. So don't be intimidated by these words. Horizontal tangent line, again, tangent line just means you need a point and a slope where the slope is the derivative. So eventually we probably need to find y prime. And finally, horizontal means that your slope is going to be 0. Because the derivative is the slope of tangent lines, we want the derivative to be 0. So all we're going to do is we're going to take the derivative and set it equal to 0 and just see what happens. So in this case, it looks like we do have to use just implicit differentiation. The hardest part is the derivative of y squared, but it's not that bad, of course. What's the derivative of y squared? Well, it's not just 2y, it's 2y times y prime. So it's going to be 2y times y prime. What's the derivative of this guy right here? Even if it looks like a quotient, don't use the quotient rule. Think about this as 2/3 x cubed and do the power rule instead. So we're thinking of this as 2/3 x cubed. When we have 3, we're going to drop it to the front. So the 3 and the other 3 will cancel each other out because they like each other so much. So then we have 2x squared at the end. So just be wary that sometimes there's different ways to take derivatives, but some ways are better than others. In this case, the derivative of 2x cubed over 3 is better done with the power rule as opposed to the quotient rule because 3 doesn't have any x terms. Finally, what's the derivative of 2x? Well, that's just 2. So it looks like we have this simple function, 2x squared minus 2. So again, what we're trying to do is we are trying to find where this function has a horizontal tangent line. So let's isolate y prime in this question. So it's going to be y prime equals 2x squared minus 2 over 2y, just dividing by a nice 2y. Remember though, of course, that if you need to, just simplify everything. Don't butcher, of course, but because all of these terms have 2's in it, we can cancel out a 2. So it looks like it's going to be x squared minus 1 over y. So now let's do the question. So the question, remember, asked about horizontal tangent lines. That means where the tangent line is horizontal, meaning that the slope is 0. Because y prime is the slope of the tangent line, what we want to do is we want to set this fraction to be equal to 0, and we want to solve some points. This question actually isn't entirely accurate. What we're trying to do is we're going to try to find at what points. So we're not only going to find the x values, we're also going to find the y values as well. So how are we going to do that? Well, if you have a fraction that's equal to 0, that just means your numerator is going to be equal to 0. So this implies that x squared minus 1 is equal to 0, so x is equal to plus or minus 1. So again, in the middle of the question, hopefully your teacher doesn't do this, I changed this to a harder question where we're not just finding the x values, we're finding the y values as well. So when you have a horizontal tangent line, you're going to set your fraction of your derivative to be equal to 0, meaning the numerator to be equal to 0. You might not have x coordinate or y coordinates yet, but in all of these questions, including the next one as well, whatever you get from the derivative setting that equal to 0, maybe the numerator equal to 0 or the denominator equal to 0, you're going to just plug whatever you get in to this guy right here, this beast of a guy, to find other coordinates as well. So let's see that in action. So again, whatever you get from this equation, setting something to be equal to 0, you usually are not done with the question, but just whatever you get, plug it back into the original. So in this case, when you plug in x is equal to 1, it looks like you're going to get y squared equals 2/3 minus 2 plus 3. So if you just quickly do this math, it's going to be 2/3 plus 1, I believe. That's going to be 5/3. Because 2/3, well, minus 2 plus 3 is 1. 2/3 plus 1 is 2/3 plus 3/3, which is 5/3. So what's y here? Y is going to be plus or minus root 5/3. Keep in mind that if you need to take square roots, don't forget plus or minus. So then we're going to plug in x is equal to negative 1. So then when we plug in negative 1, we'll get y squared. And then we're still plugging in negative 1 into this. So it looks like it's going to be plus 2 minus 3 at the end. And we're going to have negative 2/3 instead because negative 1 cubed is negative 1. So it's going to be negative 2/3 instead. Well, when we have negative 2/3, it's going to be plus 2 minus 3. Negative 2/3 plus 2 minus 3, that's going to be negative 2/3 minus 1. So that's going to be negative 2/3 minus 3/3. This is negative 5/3. So in this case, we actually get no solutions because when we take the square root, you're not allowed to take square root of negative numbers. So in this case, there were no solutions. So what's going to be my answer? Well, it looks like when I plugged in x equals 1, that gave me valid answers. When I plugged in x equals negative 1, that didn't give me valid answers. That's okay. I just ignore them. So it looks like my final answer is going to be 1 comma root 5/3 and negative 1 comma root 5/3. Sorry, when x is equal to 1, it's root 5/3 and negative root 5/3. I can't even read my answer. Because again, the answer choice 1 gave me 2 y coordinates, so 1 and the positive y coordinate, 1 and the negative y coordinate, and finally the answer choice negative 1 gave me no y coordinates. But this was a lot of work, so let me just recap it and then we'll do it again in the next video. Not the next video, but the next question. So you start off with an equation, and what they ask is, where does f have a horizontal tangent line? That means you want your slope to be 0 of your tangent line, which means you want your derivative to be 0. So the first step is just take the derivative carefully, And in this case, we take the derivative where the derivative of y, of course, needed y prime. So we got 2y y prime. And finally, the derivative of 2x over 3, use the power rule. So it's just going to be 2x squared minus 2. Then we isolated y prime and ended up getting x squared minus 1 over y. If we want something to have a horizontal tangent line, again, that means the slope needs to be 0. So what we did is we set the numerator to be 0, and we found plus or minus 1. But usually they ask us to find points as opposed to just finding x values. So no matter what you get from setting the numerator to be 0, and in the next question we're going to set the denominator to be 0, whatever we get, we have to plug into the original to find x or y's. Basically, this is a nice system of equations with substitution, where we have a very easy equation and we're plugging this in. Keep in mind though that when you plug in, you might not get solutions. Well, that's perfectly valid. So when we plug in x equals 1, we did get a nice solution of plus or minus root 5/3. But when we plugged in -1, we got no solutions, but we didn't worry, of course. So that was the final answer, 1 comma root 5/3, 1 comma negative root 5/3. Sort of a little bit antsy in the very end, but hopefully that makes sense. Keep in mind, the big thing, in my opinion, that students mess up is that once you get this equation, they don't know what to do with it. They don't know how to find y coordinates. Sometimes this will involve both the variables x and y. And what I'm telling you is that you just plug it into the original no matter what happens so that you can find both x coordinates and y coordinates. So this process isn't very bad. Setting the top to be 0 if you have horizontal. As we'll see in the next one, we're going to set the bottom to be 0 to find a vertical tangent line. We're going to get a similar equation, and again, what we're going to do is we're going to plug back into the original to finally find our x coordinate and y coordinates. So let's see that in action. So let me erase this. And what we're going to do is we're going to do this same question where we're finding points as opposed to just the entire thing, just the x coordinate and the y coordinate. And what we're going to do is we're going to find vertical tangent line instead of this function right here. xy minus y squared equals 3x. So the first step, just like normal, when you have tangent lines, basically half of any calculus exam, you're just taking derivatives a lot of times. So let's take this derivative and let's be careful. So what's the derivative of 3x? Well, that's just 3. What's the derivative of y squared? Because it has a y, it's 2y times y prime. So it's going to be minus 2y times y prime. Keep in mind though that xy, the first part of this derivative, if you want to take the derivative in order, does require the product rule, unfortunately, because it's x times y. But it's not that bad of a product rule because there's no constant in the front. So what we do is we keep the x the same. So that's just going to be x. Then what's the derivative of y? It's not 1, it's y prime. Then we do the second half of the product rule. The derivative of x is just 1 because x is the variable we're taking the derivative of with respect to. And finally, we keep the same. So this is the derivative. Hopefully you got it. Just product rule in the first step. Chain rule, of course, when you're taking derivatives of y's. Then, just like the previous case, what we need to do is we need to isolate y prime. So let's do that slowly because we haven't done this in a while. So what I do is I look for the terms that have y primes. That's the first term and the third term. And then I bring everything that's not a y prime to the other side. So it looks like I'm going to have x times y prime minus 2y times y prime. And I bring this y to the other side. It's going to be 3 minus y. Then what I do is I factor out a y prime. So when you factor out a y prime, you're going to have x minus 2y as a quantity times y prime. So we're going to divide by x minus 2y to isolate y prime. So y prime ends up being 3 minus y over x minus 2y. So this is going to be my derivative. So now let's actually use this derivative because everything up to here was just the old video, just taking derivatives implicitly, using product rule potentially, taking derivatives of y when they need it. So now that we're doing vertical tangent line, in the previous question, we set the top of this fraction to be equal to 0 because that allows the slope to be 0. Well, in a vertical tangent line, you want the bottom to be 0 so that you have an undefined slope. So in this case, what we're going to do is we're going to set the bottom to be 0 because we have vertical. So vertical says set the bottom to be 0, x minus 2y equals 0, and then you're going to get an equation x is equal to 2y. This is slightly harder than the previous example because in the previous example, it just spit out x values. But in this case, we have a relationship between x and y. And again, it never matters what you get. What we're going to do is we're going to plug back into the original. That's what students mess up. They don't know what to do with this x equals 2y, but it's not that bad. All we're going to do is take it and plug into the original. And how are we going to do that? Well, we're just going to replace all the x's with 2 y's basically. So it's going to be plug in stat to find the actual coordinates. x is equal to 2y, that's going to be 2y times y minus y squared equals 3 times 2y, because all the x's became 2y's. Then it looks like we have 2y squared minus y squared, so it looks like we just have y squared on this side. We're going to bring everything over because we want to factor everything, so 3 times 2 is 6, of course. Bringing it over is minus 6y. What's the solution of this? Because this will be equal to 0. Well, it looks like if you factor this, it's going to be, let's bring the 0 to the other side. It's going to be y times y minus 6. So it looks like I have two solutions here. It looks like we can put the solutions in this little box. Not my most organized work, but hopefully you can forgive me. So it looks like my y coordinate is both 0 and 6. Then how do you find my x coordinate? Well, we have this lovely formula right here. X is equal to 2y. So one of the points is going to be 0, 0, the origin, because when you plug in y, you'll get 2 times 0, so the x coordinate is 0. Finally, how do you find the y coordinate? Well, 6 times 2, or the x coordinate. Given the y coordinate, 6 times 2 is 12, so it looks like our second point is 12, 6, and that's the answer. So that was a long process, but hopefully I can recap it fairly quickly. What we did is we took the derivative with product rule, with chain rule as needed. We isolated y prime. If you need to find horizontal tangent lines, set the top to be 0. If you want to find vertical tangent lines, set the bottom of the derivative to be equal to 0. No matter what you get, whether that be x's, y's, or both, you're going to plug back into the original so you can find the x coordinate and the y coordinate. What happened in this question is when we plugged in 2y from right here, so it's 2y times y minus y squared equals 3 times 2y. We ended up getting the answers that y was 0 and y was 6, so that was the final answer. Because once we had 0 and 6, it was very easy to find the x coordinates because we have this relationship x is equal to 2y. So again, that's how you do these questions when you have vertical and horizontal tangent line. And sometimes these do appear on the free response questions on the AP Calculus exam, AB version especially. So again, what you do is you take the derivative. The derivative is usually going to be a fraction. Set the numerator to be equal to 0 for horizontal. Set the bottom to be 0 for vertical. No matter what you get, plug into the original to actually find points. But this has been quite a tricky process. So if you want more practice with this, and also the practice of the previous things we talked about, which was taking second derivatives and finding tangent lines, potentially even finding normal lines, what I would recommend you do is watch our Girls Teach Calculus video, just like normal. I'm going to link that in the description below, so you can check that out if you want more practice with this, especially with these harder questions at the very end, where you're finding where certain functions have horizontal tangent lines and vertical tangent lines, where those functions satisfy equations that need to be taken derivatives implicitly. But hopefully this video was useful for you. It was a nice review. Implicit differentiation is a pretty big topic on the AP exam. It consists of maybe 2 to 3 multiple choice questions and potentially one section of a free response question. So we want to get these easier questions down because we're still taking derivatives, and derivatives are our friends. So hopefully this video again has been beneficial for you. If it has, give us a like and subscribe. It definitely helps us out. But no matter what, I hope to see you next time. Thanks again for watching.